Okay, so good afternoon, everyone, and we were doing the duality, and the concept of conjugate functions will play a role in duality, and so let me. Okay, I'm here. Okay, so this is where we were. We wrote this as an optimization problem in standard form, so that's something we know. So the Lagrangian is when we add the objective function and then some lambda parameter with the inequality constraint function, and then some new parameter with the equality constraint function. So this is the Lagrangian that we form. So Lagrangian is defined as this. Okay, so the first argument is xn, and then this is for this fi, and then this is for p. So we take the objective function, and then the inequality constraint function, and then the equality constraint function, and then we have these Lagrange parameters here, lambda I and nu I. And this is the domain. So D is the domain of the objective, and then the domain of the inequality constraint and the equality constraints. And here lambda I and nu I are called Lagrange multipliers. And here lambda and nu are also sometimes called dual variables or Lagrange multiplier vectors. Okay, so there are many definitions for these parameters. Okay, so either they are called Lagrange multiplier or dual variable or sometimes Lagrange multiplier vectors. The Lagrange dual function. So we saw Lagrangian, which is this. Okay, and then there is something called Lagrange dual function. Okay, so you should not get confused with this. This is the Lagrangian. So this is just Lagrange function. And this is dual function, okay, or Lagrange dual function. So G lambda mu is the Lagrange dual function, and it's defined as the infimum of the Lagrangian, and it's an infimum over only x, okay, not over the other dual variables. It's an infimum only over x. Or if we write the L fully, then this is the infimum of this guy, okay. So it's an infimum over x only, right? So so we have to do the infimum of these x dependent terms. If Lagrangian is unbounded below in x, then the dual function takes on minus infinity. So that's obvious. If this Lagrangian is unbounded below, then infimum will make sure that it goes up to minus infinity because it's unbounded below. The Lagrangian, which is this guy, I should not write this here. Okay, so Lagrangian is this thing. So this is affine as a function of lambda and nu. Okay, so this is affine as a function of lambda and nu. Why is that? Well, this is affine in terms of lambda and nu because of the form of this. We have a lambda I here and you have a nu I here. So this is indeed an affine function. Okay, because it can be written in terms of like ax plus b form. Okay, where all the constants can be observed in this guy, and this is acting like a b here. Okay, so I can write this in that form, right? So I can define a vector f to be f1, f2, fm, and then vector h to be h1, h2, hp, and the lambda vector is lambda 1, lambda 2, lambda m, and the nu vector is nu 1, nu 2, nu p. Okay, so with this we can write this this thing, right? So this is like f naught x plus, and this is a dot product of lambda bar transpose f bar plus new bar transpose h bar. Okay, so this is of this form. Okay, so I can combine these variables together, stack these variables together, and I can also write this as f naught x plus lambda bar. So this is like a stacking. Okay, yeah, and then whole thing transpose. Okay, and then I have f bar and h bar. Okay, so it's like I stack these guys. Yeah, so this should be like a column vector. Okay, so the way so let me do this way. Okay, so lambda transpose and then horizontal stacking with the new transpose. This becomes a row vector, row vector. So all this can be taken as some matrix A, right? So f naught x plus A. I mean, in this case, it's like a row matrix. Yeah. So in this case, the variables are these, right? So I will treat this as a known quantity. So this I will call it this A, right? So this will be A. So I can also write it the other way, right? A transpose, and then these are the dual variables, right? So let us say I dual variables are denoted by D, where D is lambda transpose, new transpose. So this is hence affine. Okay, so this is just the proof of that, the fact that this is a affine in variables lambda and nu. Okay. Okay, so this is affine in lambda and nu. So what can you say about these functions, right? So how can you affine? So at least it's like convex, right? Well, it's convex and concave both, because affine functions are both. And then you are taking an infimum of these affine functions, right? So as seen as a function of lambda and nu, so this is like a affine function, and then infimum of affine function, right? So the infimum of affine function is guaranteed to be what? Right? So we know that this is like, since this is affines both concave and convex. Now the result that we know is like supremum of convex functions is convex if fi is convex functions, right? So this is the result we know, right? Now so but if we have an infimum, then what do we know, right? If we have an infimum, then what can you say about this? We know a result for supremum, right? Now if I replace this by infimum, then the same result holds for the look. If I just replace this by infimum, then can you guarantee that it's still convex? So the quiz here is f is an infimum of convex functions, right? So let us say f1, f2, fk. Okay, so if fi's are convex, is f convex? Now what do you think? Right, this is the result. Okay, this is the result we have proved before, right? Now what about this guy? If fi's are convex, is the infimum convex?
No, sir. Unless D is itself convex.
Unless D, what do you mean by D here? The domain or?
X belongs to D in.
Yeah. Okay. So the answer is correct. Okay, so it's not in general. The answer is no. Okay, so the answer is no because it can be seen from doing some quick graph plots. So let us say I have some convex function like this. Okay, and another convex function like this. Since these are ball shaped, I know that these are convex, right? So let us say this is F1 and this is F2. So F1, F2 are convex, right? And I'm supposed to take the infimum, right? So these guys like keep going there and these guys keep going there. Supposed to take the infimum. So lower value, lower of the F1 and F2, right? So lower up to here is these guys are lower. And if this is the tipping point, crossing point, and then here from here onward, these guys are lower, right? So I have to take these lower values. So the f function in this case will look like this now. Okay. Now the question is this convex? It's clearly not convex, right? Because line joining is below the curve. That's not the definition of convexity, right? So we have to be a bit careful. Supremum of convex functions is convex, but infimum of convex functions may not be convex. However, if we change this to concave, then infimum of concave functions will be concave. Okay, so this can also be proved right from here because supremum of these functions, how can I write this in terms of infimum, right? The supremum of this function can also be seen as like infimum of minus of f1, f2, fk, right? So, but minus of a convex function, minus of a convex function will be what? So is minus of a convex function concave?
Yes.
Yes, right? Yeah. So so from here, like we can write down what we are sure about is the following. If f is infimum of f1, f2, fk, then this implies f is concave if fi's are concave. Okay, so this is like the different the concave counterpart of this result. But in this case, what we have here, if you see, this is affine. So this is like both concave and convex. But but if we take the infimum of these affine functions, if we take an infimum of this, okay, so let us clear this out. Yeah, so if we take an infimum of this, and I know that infimum, and this is like concave and concave and convex, both. But since we are talking about infimum, what I am guaranteed about, since this is infimum and the inside functions are concave because it's affine, one thing is guaranteed, that this is going to be like this is going to be concave. Okay, so g lambda nu is going to be concave. Okay, so even when the original problem is not convex, now that is very interesting, right? So I did not say anything about there was no assumption made on the objective function or the constraint functions such as inequality constraints fi and equality constraint functions hi. No assumption was made on the convexity of any of these fi or hi, okay, including the objective. Okay, so no such assumption was made, but we end up having the dual function being concave. Okay, so dual function is guaranteed to be concave. Okay, now still, like so far we have defined the dual Lagrangian and we have defined the dual function, and the question is why dual function is important anyway, right? Even if it's concave, how does it help, right? Okay, so far this is what we have. Now let us now look. So to see the importance, like one of the things that you can already see why the dual function is important is given by this bound. Okay, so the lower bound on the optimal value. Optimal value, when we talk about, it's with respect to primal. Okay, so primal variable, that is in a primal variable in our case in this course usually we denote it by x variable. So this is f of x star. Okay, so the optimal value obtained at the optimal point x star. Okay, and what this relation tells us is that the dual function, if you get hold of dual function somehow, okay, and then that gives you a lower estimate of your primal optimal. Okay, so that gives you dual estimate. So what we are usually talking about is the infimum. So our p star is here, and we are doing a minimization in the primal, right? So in the primal domain we are minimizing, right? So we are minimizing. So naturally any random point x0 we start with, okay, is going to most likely, it's very rare that you will hit x star directly, right, at one step. So you will start with something that is like giving you some value of p0, and then you will apply some iterative method, and then you will try to converge to this. So you are approaching p star from the higher value to lower, right, from higher to lower. But what is interesting is like the dual function is telling you the lower value. So it's telling you the lower bound of this. So it's telling you what is the lower value. I mean, if it is a worse value, then maybe it's too loose estimate. You can say that, okay, g lambda nu is here, and then you can say, okay, what is the use of this? But nevertheless, it's telling you some lower bound. Okay, g lambda nu is indeed telling you some lower bound of, in other words, if you have some estimate of this guy, and if you are using some iterative method, and if you have hit this guy, if you are getting very close to this guy, then it is also telling you that you are actually very close to this guy, p star. So in other words, this is an indirect way of you knowing that, because in the iterative method, you are going to go in this direction, and if you are getting closer and closer to this guy, and this being a lower bound of this guy, in other words, it's also telling you that you are indeed getting close to this. Okay, so having an idea of this is helping you, because in general you don't know this. You now remember that getting an estimate of this itself is may not be easy. Why it should be easy? Because, right, so it may not be easy, right? Because this is a function of lambda nu, and then getting some general estimate of this may not be easy at all. But in case if you have an estimate of this, then the primal algorithm that you are following to reach here, if in case you are getting closer to this, then you are happy, right? So in fact, if in case if you hit this, then you must hit the p star. Okay, because this has to be the lower bound of this. So in case you got to, let us say, 10 to the minus 10 accuracy, then it's telling you that you are even closer to p star then, because you are already closer to g lambda mu with an accuracy of 10 to the minus 10. So what I'm trying to say in general is like dual can give you some lower bound. on this, and this may be used as a reference. Of course, big question is it easy to calculate this, right? Okay. So how do we prove this result, right? So why should the dual function be a lower bound of this? Okay, so let us now prove this. So suppose some x tilde is a feasible point, and we know that a feasible point is a point where the inequality constraint is satisfied. That is, fi x tilde must be less than or equal to 0, and equality constraint must also be satisfied. Okay, lambda are always greater than or equal to 0. That's the definition that comes from the Lagrange multiplier assumptions. Okay, so this lambda is greater than or equal to 0. Then what do we have? Like, so since these guys individually are less than 0 and individually are equal to 0, if I do a sum of these, so m sum of these and the weighted values of lambda I, where, so this is like a vector lambda I we mean, okay? So lambda 1, lambda 2, lambda m is greater than or equal to 0. So entry wise they are greater than or equal to 0. So that is lambda I are greater than or equal to 0, and yeah, mu I we don't need to assume anything anyway, because this is sitting with the equality constraint. So this will be equal to 0 anyway, because these are all equality constraints. But what is more important is here. So this guy is equal to 0. Okay, and this guy is lambda is greater than or equal to 0 times fi x tilde is less than or equal to 0. So overall it is less than or equal to 0. Right? So the sum, this overall term, okay, these are all less than or equal to 0 because individual terms are less than or equal to 0, and this is like equal to 0. Okay, so this is what we have. Remember, we are supposed to prove this, right? So, and we know that this is infimum of the Lagrangian, right? So two terms of the Lagrangian we found, and we also need an objective term, right? Okay, so we also want to know f naught x tilde, right? That will be the whole Lagrangian, and then we have to do infimum of that. Okay, so I've written all these steps together here. So let us look at the Lagrangian at x tilde, which is the feasible point that we have chosen. Okay, and this is like arbitrary point, right? X tilde is arbitrary, although fixed. So x tilde lambda nu is f naught x tilde, and then this guy, and then this guy is the same as above. Now this guy and this guy is less than or equal to 0. Okay, so if this thing is less than or equal to 0, okay, so this implies that the sum will be less than or equal to f naught x tilde. Okay, so that's clear. Then let us look at now g lambda nu. G lambda nu was infimum of the Lagrangian, and so infimum must be less than or equal to some arbitrary value, because this is the infimum. This is the minimum possible value that you can get. It must be less than or equal to L computed on some arbitrary value. Okay, so this is less than or equal to L infinity L x tilde this, and then we know from above. So this is from star. So this is from star that L x tilde lambda nu is less than or equal to f naught x, and this is true for any feasible x tilde. Okay, so what we have found is this: g lambda nu is less than or equal to f naught x tilde. Okay, in other words, this is less than or equal to any objective value that you get, right? So this is true for any x tilde. So this must be true for infimum of that also, because no matter what x tilde I take, okay, it's always less than that. So it must be less than the infimum as well, minimum possible of this as well. Okay, it may be equal. That would be the best case. But in general, what we can say is less than or equal to the p star, which is the optimal value. Okay, so this is the proof of the lower bound. Okay, via the dual function. Okay, so now let us now look into these problems. So we are in the chapter 5 duality, like we are in the midway. of this, and then we will quickly cruise through the algorithms in the remaining lectures. Algorithms are like easy. The main thing, the maths part, is where I have to spend a little bit more time. Okay, so here consider the following optimization problem. Okay, let us check what we learned so far about the Lagrangian, the dual functions, the concavity of that, and the lower bound estimate. Okay, so let us try to work through some examples so that you have some idea of how to deal with these things. Okay. Okay, so the first question is find the Lagrangian. Okay, Lagrangian is a straightforward, because in Lagrangian we take the objective and then we put this in standard form. So B will go on the left hand side, right hand side must always be 0 for both equality and equality constraint. We multiply it with this parameter nu. So nu is the parameter that goes by convention. Mu goes with equality constraints, and lambda goes with inequality constraints. So in this case, we don't have any inequality constraints. So lambda parameter will not show up anyway. So only nu will show up in this case. Okay. So Lagrangian we can write, and then we have to find the dual function. The dual function is g lambda nu, and that will be infimum of L x and nu only, because in this case the lambda is not there, so we don't bother to write lambda here, and this is infimum over x. So this is the second part. Third part is whether the dual function is concave, but only when we have found this. In other words, we have to solve for this infimum problem. Then we will see whether this is a, so there again lambda is not there, so this will just be a function of nu. Okay, in this problem, and then we will see whether g nu is a concave for this example, and we will check whether we have found some lower bound. So this will serve as a lower bound for P star. Okay, so this is the problem we have. Now let us try to write down things. So the first step is Lagrangian. So Lagrangian in this case is given by L x nu. Only nu is there. Only equality constraint is there. So this is the objective function x transpose x plus nu times b. Don't forget to put b on the right hand side. Okay, so plus nu transpose ax minus b. Okay, and the domain will be the usual. It will inherit the domain of that we have described. So apparently this is defined over all Rn. Okay, Rn and then Rp. Okay, so the domain will be Rn times Rp. Okay, and so this is the Lagrangian. The first question is solved because this is done. Find the dual function. So dual function is, since in this case it's only mu equality constraint, so we have to do the infimum of x and then Lagrangian of x nu. Okay, there is something Lagrangian also used in physics. I think the better way in optimization is like to say Lagrange function. Okay, but anyway, should not get confused. So infimum of x and then Lagrange x nu. Okay, so we have to find the infimum of this guy, right? So we have to find infimum of this x transpose x plus nu transpose ax minus b. Okay, so this is the function for which we need to find the infimum. In the infimum, there are terms which has no dependence on x. Now that can be pulled out, right? So those terms, so nu transpose x or minus nu transpose, sorry, b. Okay, mu transpose b can be pulled out, and then I apply infimum on the remaining terms, which is x transpose x plus nu transpose ax. Okay, so our problem is to find infimum of this, right? Now now what is this term? Right, so we have to find infimum of this. So what is the nature of this, right? Have we seen functions like this before? Right? So which type of function is this? Right? We have written things like this, right? So what are the powers of x in this? The maximum powers of x. These are square terms, right? 2, right? So this is which function?
Quadratic.
Quadratic, yeah. So this is a quadratic function, a quadratic form. Okay, sometimes they call it form also. Okay, it has some use in so-called differential geometry and so on. Okay, so sometimes the term is used as form and so on, but for us it's just a quadratic function. And okay, and we are supposed to find a infimum of a quadratic function. This is differentiable. Okay, naturally is differentiable. Okay, quadratic functions, it's a polynomial, or a polynomial are infinitely many times differentiable, right? Okay, so we know how to find the infimum of this, right? So to do this, what we can do is like, so in terms of L also we can write, okay? So to find the infimum, we can take partial derivative of this, the gradient of this with respect to x, and equate it to 0, right? So what I can do is L x nu. Now this has no dependence on. So I can look directly here, right? Because I have to solve the infimum problems. I can just look here as a function of x, and then this is quadratic differentiable. Okay, and okay, one more thing. So what about, is this convex? Is this convex also, right? So what was the condition for convexity? What do you think? It is
Second derivative.
Yeah, second derivative test, and it is convex because second derivative will give us identity, right? Yes, so the answer is yes, by second derivative test. Okay, in other words, grad x square L. Okay, if we do, we get identity, and identity is positive definite. Okay, so it is convex. Okay, so the definition that we have seen is like, if a function is convex, then the optimality condition is given by grad of f equal to 0. So this is what we are going to do here. It is enough to find where the grad is equal to 0, and that will give us the critical point, and that must be the minima because the function is convex. So that must be the minima, right? Okay, so this equals to 0, we have to solve for, right? So this implies what, right? So we have to take a gradient of this with respect to x. So if we take a gradient of this, then we will get 2x. So I hope you have done some practice of vector and matrix derivative by now. And then plus, if I take a derivative of this, now this term will gamma nu transpose b will be 0. There is no dependence, and derivative of nu transpose ax, okay, is a transpose nu. Okay. Okay, verify this. Okay, so if this is the case, okay, so this is the condition we have, and from here I can solve for x. So x is minus half of a transpose nu, right? So this is the place for which, this is the value of x for which I get the infimum, right? So I can substitute this back and I can get rid of x, and I get a value in g nu only, right? So this implies g nu is, so I put the x star value for which this infimum is achieved. In other words, I have minus half and then a transpose nu and nu. Okay. Okay, so now I have to evaluate this here, right? So what do we have, right? So we substitute x here, right? Now, do we see some term here and then some connection with this guy, right? So let us work out. I think it seems like it may be simplified further. X new is x transpose x plus nu transpose ax minus b. This is x transpose x plus nu transpose ax minus nu transpose b. Now, do we see something here? Well, so let us say this is 1. So 1 implies if so what do I need? I see A transpose nu, or I can also reverse this. But here I see nu transpose A and then multiplied by X. So it seems like if I multiply by X transpose X here, I see some relationship between these two guys. So this implies X transpose X is minus half X transpose A transpose nu. Remember that this is just a number. Okay, so this implies X transpose A transpose nu is minus 2 of X transpose X. Right? So in other words, like this guy can be substituted with minus 2 X transpose X. So this guy will become now minus, so X transpose X and minus X2 X transpose X. So this will be minus X transpose X and then minus nu transpose B. Okay, so this the Lagrangian like simplifies to this. So I only bother putting X here now. Okay, so X is this guy, right? So minus half A transpose nu, this transpose minus half A transpose nu, right? And then these things have no dependence, so they will just remain like this. Okay, so if we simplify this further, yeah, I have some space here. So if we simplify this further, then G nu is, so it will become minus 1 over 4 mu transpose A transpose. Okay, so this is minus 1 over 4 mu transpose A transpose nu minus B transpose nu is whether it was this term was there, right? Or this term here. Okay. So we found the dual function also. Okay, so that was this part of the question. Now check whether the dual function is concave. Is this concave? So what do you think about this? Is this concave function and how? We have already proved before that dual has to be concave. Okay, we have already proved the general statement, but in this case, if someone asks you to prove this function is a concave, what do you do? This is again quadratic form, right? Because this is like the matrix P. Okay, and yeah, this is just a like some B transpose the variable here. Okay, so this is like B transpose X. This is like X transpose PX and so on, right? Okay, so this is like a quadratic function, right? Again, remember that quadratic function appears a lot in modeling. Okay, in various type of models, you will see quadratic functions are very common. So this is a quadratic function and differentiable. Okay, so quadratic function differentiable. So we can apply the second derivative test. So by second derivative test, we find that grad nu square of G nu will be just minus of 1 over 4. We will be left with A transpose, right? Okay, so is this negative definite. If you have to prove that this is concave, then we have to prove that this is negative definite. It is true because this is less than equal to 0 because A transpose is always positive definite. Okay, for any A. Okay, so A transpose is always positive definite because I do X transpose A transpose X. Now this I can write this as AX transpose AX, which is norm of AX. Okay, so this is like squared, and then but norm is greater than equal to 0, right? Always. So this is true for all X. This implies AA transpose is symmetric positive semi-definite. Okay. Okay, so since the second derivative test is always less than equal to 0, this implies that G as a function of nu is concave. Okay, now check whether the dual function is a lower bound to P. So the dual function is a lower bound to P star. Okay, so by the result that we had before, what we can claim now is that this is supposed to be the lower bound of the primal. Okay, so it's supposed to be the lower bound of the primal. In other words, from the lower bound property. Okay, so let us write this here. So from the lower bound property, what we can write now is a -1/4 nu transpose A transpose nu minus B transpose nu gives us the lower bound of the original function, which was X transpose X subject to AX equals to B. Okay, so this will serve as a lower bound. So this function values will serve as a lower bound for this. In other words, you can test on some values. Okay, you can test on some values, and that will serve as a lower bound for this. I mean, another way to look at this would be, can you like maximize this? Okay, and that will give you a better lower bound of this. And in fact, this is already the main idea behind duality. Is like you try to find the optimal, but you find it by making the G function, the dual function, maximum. Okay, so now you see that to reach P star, the primal way is like to follow from here, but you form a dual. Okay, so G nu lambda, and this is less than equal to, but if you make it supremum, okay, then provided some conditions are there, then either you come via this way, primal way, or either you come via the dual way. There may be like these are like two different ways of solving your problem. You change your problem to dual, and then you solve a maximization problem. The nice thing about the dual is that it's a concave. Okay, although your original problem F may not have been, so minimize F may not have been like concave or convex nice form, but since you went to the dual, it is a nice concave form. So, and you can make a minus of that and it will become a convex, and then you can use some convex optimization solver. Here you were not sure what to do, right? Because it was neither given to be convex or concave, so you don't know, right? So this is already giving you a hint to how to solve a given problem via the dual. Okay, so far what we are seeing is like this is giving me a lower bound, and if it is not at all easy for me to find the supremum of this, one thing this might tell me is give me some hint about the lower bound, some hint about the lower bound, in the sense like I can substitute some values of mu because A and B are known. Okay, so let us say in this case would be some nu could be some lambda min or the smallest eigenvalue of A transpose. Okay, or the eigenvector of A transpose, then it will spit out some number. Okay, and that number can tell me what could be the possible lower bound of this. Okay, so all this makes sense when this is a nice form, and then like certain values give me an idea about the P star. Okay, but as I said, this is still a lower bound. Only when you make it supremum, then you are actually close to the P star that you need. Okay. Okay, so this was about this problem. Now let us look into some other problem, just a little bit more practice of the dual form. So far what we are focusing on in modeling. Okay, so this course is divided into two parts: modeling and algorithms, solvers. So these are all models, like optimization problems show up in different form. We are trying to write this into different forms by taking use of also duality and so on. And later we will see how to solve this. Okay, so this is the linear LP. Okay, so the linear programming problem, and so what is the Lagrangian in this case? So we have inequality constraints, and you have equality constraint and inequality constraint. So we can form the Lagrangian. What is the dual function for this? And check whether the dual function gives the lower bound to P star. Okay. So let us now try to find the Lagrangian for this. Okay. So the Lagrangian for this will be the objective. And then remember that this is not really in the correct form. Okay. The inequality constraints must be less than equal to 0. So must put in less than equal to form. But this is easy in this case because I can just do minus x is less than equal to 0. I redefine my fi's. So redefine my fi to be minus x. Okay. Or like xi. Okay. So these are like x greater than equal to 0. It could be seen as like individual components of x. So minus xi less than equal to 0 for all I equal 1 to whatever is the length of n, let us say n length vector we have here. Okay, so these minor things you should not forget. Okay, because Lagrangian is only defined on the standard, I mean the optimization problem. I don't know why I wrote in like this, because this is not, this should be less than equal to form, then we call it in standard form. Okay, so so at least we can think of this as LP, or we can always convert this into a standard form. So it doesn't harm even if I say standard, because it is equivalent to a standard form. Okay, so the Lagrangian we can form. So let us write down the Lagrangian. In this case, we have both equality and equality constraints. So both lambda and nu parameter will show up. So Lagrangian is Lx, lambda and nu, both are there. Objective is C transpose X. And then inequality constraint is minus xi less than equal to 0, right? So minus, and the parameter that goes with is lambda I and xi, and I equal 1 to n. Okay, n length vector plus nu transpose. So this minus came because of this minus. So minus I took out here, and mu transpose, and then the equality constraint. So equality constraint, I have to put b on the left. Okay, so this is ax minus b. Here I wrote mu as a vector. Here I wrote lambda as element wise. Okay, so lambda, these are the ith component of lambda vector. Okay, it is a good idea to keep out the non-x term. So this is like minus nu transpose b plus, and then Yeah, so this can be written in a vector form together because x this is inner product of lambda with x, and this is already written in the inner product. So my goal is to take x common. So I can write this as C plus A because I want to take a transpose after that. Okay, so I can write A transpose nu and then minus lambda and then whole thing transpose. So you can say that this is this comes out to be the remaining term here. So this is the Lagrangian. It's a good idea to keep out the non-x term so that we have a clean view of which are the x terms and so on. Okay, so this is the first part, and the second part is the dual function. So the dual function is g lambda nu. Remember, dual does not involve x, right? Because we infimize over that. Okay, that's why we don't include x. So this is infimum of x L x lambda nu. Now this guy, the non-x term will come out of the infimum. So minus nu transpose B, and then plus infimum of the remaining x terms, C plus A transpose nu minus lambda transpose x. Okay, so this is the infimum over this guy, right? Okay, now usually we want to solve for this infimum, right? We want to see this only as a lambda nu. So in other words, we need to solve for this infimum problem. So what is the infimum of this, right? So the first question is like, what is the nature of this? Now here lambda and nu both are there. So which type of function is this, right? So the question is which. So remember previously we saw quadratic, right? Now we are asking for which type of function is this? Function is this. Okay, which type of function is this? Linear. It's linear. Okay, so the answer is linear. Linear in nu and sorry, not linear. And we are talking about linear in the variable x because we are solving for x, right? So linear. We always know that the dual function is linear in lambda and nu. That we already know. When I'm talking about infimum, then I have to think about x. So it is linear in x. Okay, so this is a linear function in x. What is the infimum of a linear function? So what do you think will be the infimum of a linear function?
Minus infinity.
Minus infinity provided
Given that multiplier term is non-zero.
Given that multiplier term is non-zero, exactly. So so we can write this, right? So infimum of x is C plus A transpose nu minus lambda. So this is equal to minus infinity if this term is non-zero. Okay, so something like this we have like seen, I think, in the context of maybe conjugate function. So this guy okay is non-zero. Okay, so then we can make it go to minus infinity. The only way it may not go to minus infinity is when this term is equal to 0. In that case, it will be 0. If C plus A transpose nu minus lambda is equal to 0. Okay, so So the interesting case is when this happens, because if it is minus infinity, okay, it will take everything to infinity, right? So the interesting case is when this happens, right? So now we can talk about the dual function. So overall dual function will be what? So dual function will be equal to just this, because when C plus A transpose mu minus lambda will be 0. Okay, so in this case the infimum will be 0, and otherwise it will be minus infinity. Okay, so we can now write about G infinity. We can now define G lambda infinity. This implies G lambda nu is equal to so 0 plus, right? So this 0 plus minus nu transpose B, right? So this will be minus nu transpose B if C plus A transpose nu minus lambda, C plus A transpose nu minus lambda is equal to 0. It is minus infinity otherwise. Okay, so it's minus infinity otherwise, and we have defined the function G now completely. Okay, there are like I mean there is no dependence on X here. Okay, so that's why it's completely dependent on this is like only a function of lambda and nu now. So what we observe here is that G lambda nu is finite. So finite meaning this guy, assuming that B and nu are finite values. So is finite only on a proper affine subset. Affine subset of Rm Rp. When I say proper affine subset, which subset I'm talking about? This guy, right? So this condition is giving me the affine subset, some affine subset, because this is like a linear system, right? So this is like a some kind of a plane, okay, in mu and lambda variable. Okay, so which forms an affine subset of a ambient space, which is Rm and Rp, because nu is Rm length and lambda is P length, right? Or maybe the other way. Yeah. So this is finite only on this, and then okay, and this will be a very common occurrence actually. Okay, this will be a common occurrence because of the fact that nu and lambda that we see in the dual functions, they happen to be linear form, right? So the conditions that we get will be very commonly like this. Okay, so the dual functions will be very commonly be having some valid non-infinity values when on some affine subset, because the moment we get a relation like this, because nu and lambda, according to the way dual functions are defined, they are always going to give me something linear relationship is there. The only thing that will change is what is the nature of this X variable, right? So this also has some role to play, but given that a mu and lambda are like linearly related, very often you may encounter this. So your dual function may be finite on some affine subset. Okay, so that's why we will say that it's a very common occurrence to see things like this. Now the lower bound property. So lower bound property was just G lambda nu must be less than equal to P star. Okay, so and this is non-trivial. Like Trivial case is when it's minus infinity, so minus infinity less than equal to anything. So this is like non-trivial. So this is non-trivial when we have actually this case when lambda greater than equal to 0, which is always the case in the Lagrange, and then A transpose nu minus lambda plus C is equal to 0, which is this case. Okay, so which is this case, in which case we can write that in which case we have minus nu transpose B. So minus nu transpose B is less than equal to P star. So this is worth looking at. So this lower bound may be more useful than this minus infinity, right? Okay. So this is another way where we also get another lower bound for the LP. Okay, for the linear program, we got the lower bound on the optimal. Okay, let us do one more practice problem on this. So this is all part of modeling, right?
Can you repeat, sir? Hello, sir.
Yeah.
Can
Yes.
you repeat the lower bound property once again?
So lower bound property is just written here, right? This is the lower bound property. The dual function.
No, sir. For the previous question, yeah.
Yes. Hello. This is the lower
for
bound.
this.
Yeah, this is the lower bound property for this, and in the previous case, yeah, in the previous case, the lower bound was this minus nu transpose B. Okay, because that was only dependent on nu. So nu transpose B is less than equal to P star for this problem. Okay, your sound is not clear, but I hope what you said is what was the lower bound property for the previous problem. So that was the lower bound property for this problem. So nu transpose B must be less than equal to P star. And yeah, it turns out that they are same actually, right? No, not lambda. So this whole thing, right? This whole thing is less than equal to P star. Okay, so this is the lower bound in this case is a different. You have this thing less than equal to P star, but lower bound property in this case is just this minus nu transpose B. Okay, so I hope I understand your question correctly. Okay, now we can do one more practice of this, and perhaps few more will show up in your assignments. So let us see the lower bound. I mean the Lagrangian dual and the lower bound property for this. And this is called two-way partitioning problem. And the reason why it is called a two-way partitioning problem is because of these constraints. So let us try to observe few things. So observations here are the constraints restrict the values of xi. So constraints restrict values of xi to plus minus 1. Okay, so x can be either plus 1 or minus 1 in this case. The problem is equivalent to finding a vector with components plus minus 1, and that minimizes this. Right, so this is the same thing as this is just another way of saying that. What about the feasible set here? Okay, so feasible set is obviously the set of all x. Okay, so let us say in Rn, and well, you can talk about Rn, but x is only taking plus minus 1 value, right? So I can say Rn, but it's better to restrict to just plus minus 1 value, right? Boolean. Okay. So x is in Rn such that Yeah, so xi square is equal to 1 for all I equal 1 to n. Okay. So what about the cardinality of this feasible set? So what would be the, like, what do you think will be this?
2 power I.
2 power I, oh, where is I here? N, right? 2 to the n, right?
Yes.
Yeah, so cardinality of this feasible set will be like 2 to the n because x has those choices, right? So cardinality of S will be 2 to the n. Each entry can be 1 or minus 1. There are n entries, so 2 to the n, product rule, right? Okay, so cardinality is this. So this is finite feasible set. All right, so this is a finite feasible set. But does it mean that, so if this is a finite feasible set, why don't I just substitute these values one by one and find the answer? Okay, so since cardinality of is finite, can test x transpose wx for all x, right? Well, it is finite but exponentially growing, right? So but this grows exponentially, right? So this is why it is not even combinatorially not possible now to just substitute these values, because for a large n, your algorithm has to now the time complexity will grow exponentially, right? At least this is what it seems for the moment. So these are the observations we have. So it's not really a good idea to do this testing one by one. Okay, so we need to think about some proper way. So what do we do? Right. Another thing is like why this is called two-way partitioning. So why two-way partitioning? Why is this called two-way partitioning problem, right? So it is a partitioning problem because in some sense we are asking for a partition of the set. Okay, so it's like a partition of the set of mn elements. So it is like partition of set of n elements. So in the sense that one partition goes with +1 entries and another partition is assuming -1 entries. Okay, so it's like a set of n elements and some goes with 1, some goes with -1. So the feasible set X in this case, so I can write it here. So this can be partitioned into set of all I such that xi is equal to -1 union the set of all I such that xi is equal to 1, right? +1, and this is like -1, right? So and the matrix wij can be interpreted as cost of having I and j in the same partition. Okay, it's cost of I and j in same partition. Okay, so and then similarly -wij can be interpreted as the cost of I and j in different partition. In other words, overall overall the problem looks like partition with the least cost. With least cost. So you partition these xi and yi in such a way that this whole cost is minimized, right? So we are supposed to minimize this. So which component of x? Okay, so that's like -1, 1, -1, -1, 1, so on. And then I have a w here. And then I have, let us say, -1. So this is like the same, but the transpose of that here, right? So it's like 1, -1, and so on. So where I should choose 1 and where I should choose -1, such that the overall sum of these values is the minimum. Okay, so it's like yeah, so it's like which parts of the x I put in -1, which part of the x I put in +1, and then I can separate out the minus values. So minus values I separate out, and then I separate out the plus values, and I separate out the plus values and plus values, and then this will this will give me one cost, and then the minus values will give me another cost, and then I'm asking for what is the total cost of all this combined. Okay, it's like what is worth doing, right? So which partition should I have more minus and which I have plus, and so on. And that is why it can be seen as two-way partitioning problem. So this is still abstract, but given an application, you can give a more concrete meaning to these terms. Okay, so so our goal is to find a partition with the least cost. Okay, so which partition of -1 and +1 will give me the least cost. Okay. Okay. So now we can write down the Lagrangian. So what was the problem here? So problem was this, right? So we have only equality constraints here, and we have to put 1 on the left, and that will give us the equality constraint functions hi. Okay, so we have everything there to write the Lagrangian. So the Lagrange function is given by L, and since there are only equality constraints, I have new variable only x transpose wx plus, and then since these things are given in component form, I will write this in the sum form, right? If it was vectorized form, then I just write in vectorized form. But if it is given in the individual terms, then I prefer to write this in the individual term, in the sense that nu I, and then what was the equality constraints? Xi square minus 1. Okay, times xi square minus 1. That's all, and I is 1 to n. Okay. So now let us see if we could, because whenever we write this Lagrangian, we want to see where are the x, because x terms are from where we get the dual, right? So we always look out for x. So x is here and x is here. So and I see xi square here. So I sense a quadratic form here. Okay, so I can sense a quadratic form here. And this means that it can be written in the form x transpose sum p times x. Okay, since I see the square powers. So let us try to see if we could do that. So this is like x transpose, I take common w, and then plus, and overall this we sense this as a quadratic form. Okay, so for the moment we can put a question mark. Okay, so here now we can continue from here. Since we want to see this overall as a quadratic form, we want to write this in this compact form x transpose px. So then let us take common x transpose, and in the p we have first term is w, and then nu I, right? So nu I, but I want to see this as a matrix, right? So how can we see these terms, right? Nu I xi square. I know that this I can write this as xi like this, but this nu I is here, right? So
Diagonal matrix.
yeah, make a diagonal of that. Okay, so what I can do is like I can do nu 1, nu 2, and nu n. Okay, so 0, 0 here. So we can do this. So now one x comes from here, it goes with nu, and then another x now will come from this side. And then the non-x terms will be summation of nu I and 1. So summation of, so basically this is minus of, so the remaining term is minus of nu I. But this I can vectorize this in the sense that it is like multiplying with a vector of all 1 transpose the new vector, okay, where 1 is the vector of all 1s. So then if I do a inner product, I get a sum of the vi, okay, nu I, okay. So I can compactly write this 1 transpose nu, where, so those who can't watch video, let us write down explicitly. So this is like 1, 1, 1, all 1, okay, vector of all 1s. Okay, and nu is also well known, okay. So nu is, okay, 1 is this, so 1 transpose will be a row, nu 1, nu 2, and nu n. Okay, so we have written this in the quadratic form, right, where we see the matrix P as this guy. And this is useful because then we can immediately like try to guess, right, whether this is a convex and when, under which condition it will be convex, and so on. So that was the motivation behind this. Okay, now this was Lagrangian. Now let us write down the dual function, right? So dual function is, in this case, since this is only equality constraint function is there. So this is the same thing as saying infimum of x and this guy, right? So this guy is x transpose w, and one of the notations that we use is something like this. So make a diagonal matrix out of a vector. Okay, so sometimes this notation is used to make a diagonal matrix from a vector. Okay, and our focus of the infimum is only here, obviously, because other term has no x. Okay, so what is the infimum of? Now we know that this is quadratic. Okay, so what is the infimum of this, and what are the dependencies on this matrix? Right. So these things will help us to find the infimum of this guy. Right. So what do you think? What would be the infimum of this guy? This is a quadratic, right? And if this guy, since time is less, okay, let us do this quickly. So if this guy is positive definite, then the minimum value is going to be 0. Right, because if this guy is positive definite, then the minimum value is going to be 0. So infimum of a quadratic function is 0 if the P matrix, this is the P matrix, is semi-positive definite. Okay, all right. Otherwise, it's like greater than, because we know that x transpose px is greater than or equal to 0, and if P is positive definite, is semi-positive definite, then we know that this is by definition this holds, right? So the minimum value is obviously 0 only, right? Okay. So minimum value is 0. So in that case, this will be 0, and then only this term will be remaining. Okay, provided this term, this matrix is positive definite, and if it is not positive definite, then no one will stop this guy from going to infinity, right? Because if it is not positive definite, then what will happen is, like, let us say this is our P, okay, since I'm using this P here. So if P is not positive definite, then what will happen? There will exist if P is not positive definite. Okay, let me write down here. Okay, so if W plus diag of nu is positive definite, this is the definition of positive definite, then this implies G nu will be, this will be 0, then this will be minus 1 transpose nu. And if W plus diag of nu is negative definite, so this is this, then G nu will be minus infinity, because if W plus diag nu is less than infinity, this implies there exists X such that X transpose W plus diag of nu X is less than 0. But if that is the case, then I can keep scaling the X by a positive quantity, and I will keep making this more and more less than 0. Okay, so I can make this, so I can substitute X equals to some beta y is equal to some beta X. Okay, and then we can make this as beta tends to positive infinity. This implies Y transpose W plus gamma X tends to minus infinity. Okay, so this will become unbounded. Okay, so hence we got the values of P, and then I think I'm almost, so so this implies, to wrap up, minus 1 transpose nu if W plus diag of nu is positive definite, and this is minus infinity otherwise. And the lower bound, the usual lower bound, like if this, we consider this the usual lower bound for the primal will be given by this. So minus 1 transpose nu is less than equal to P star. Okay, so in this two-way partitioning problem, this is the lower bound on the the minimum value that we get. Okay, so I think we can stop here, and we can continue this in the next class. So we have like little bit left for the duality, and I think, yeah, and then after that we will get into some specific models after that. So we will look into models given by SVM, support vector machines. We will look into recommender systems. So now we will look into neural networks, recurrent neural networks. What are the models that they give? Okay, some concrete examples from there, and reinforcement learning models there. The basic, okay, my goal is not to go into the detail of those things, but just to see from optimization point of view, what is the modeling part there. And then finally, we will see in like 5-6 lectures, we will go through the algorithm part. Like, so many models are there, and then we will see how we go about solving these models. Okay, so that will be the solver part. Okay, so this is how we will try to end this. Okay. Okay, then, so I will stop here, and if there is question, then I will be here, and you will have a quiz, I guess. So do try to revise things. Okay, a quiz will be multiple choice, and I think it's 28 or something, right? Okay. Okay, then, so I will stop here.
Hello, sir.
Yes.
Sir, can you go